Okay, good. Okay, so today, so I'll continue the presentation about bump, and we'll start with the NICAS smoother, and then I'll talk a bit about the how to use bump in the OOPS JEDI framework. So let's start with the NICAS smoother. So the goal of this smoother is to get a generic method to apply a normalized convolution operator, and this operator will be used to implement either a static correlation or a localization in a variational DA framework. So by generic, we mean that it should work on any grid type. So the standard methods for this kind of operator, they have drawbacks that we want to avoid. For instance, if we use spectral or wavelet transforms or recursive filters, we will need regular grids. If we use implicit diffusion, we can work on any grid, but it's and we can also take complex boundaries into account, but it's very costly, and the normalization is not an easy problem. So just to make sure I'm clear about normalization or normalized, it means that the diagonal of the convolution matrix we apply is 1. So 1 for every diagonal coefficient. And it is very important if we want to apply a correlation operator or a localization that doesn't change the variance. And it's not an easy problem actually to solve to get these normalized operators. So here we want to take advantage of an explicit convolution operator that we will denote C. And this convolution should work on any grid, and it should be exactly normalized, so have the diagonal coefficients equal to 1. If we just define a basic convolution operator on the full model grid, since it scales as the square of n, where n is the size of the model grid, the cost is just too big. So we will have a first trick, and it's to limit so it's to use a subgrid. Here it's with the green NS, so we just subsample the full grid, and we define the convolution operator on this subsample grid. To go from the subgrid to the model grid, we define an interpolation. It's the red S here, and its transpose is also used to approximate the full convolution operator C. So if the size of the subgrid is a lot smaller than the size of the full model grid, then the total cost actually scales as n, because it's only the interpolation cost. So this is interesting in terms of cost, but there are a few issues with this approach. First, if the subgrid density is too coarse when we compare it to the convolution length scale in CS, then the convolution will be distorted. So we cannot have something too cheap, or we will just distort the function we want to apply. And second, we break the normalization because of the interpolation. So even if CS, so the convolution operator on the subgrid, is normalized, so even if the diagonal coefficients of CS are 1, the diagonal coefficients of SCS S transpose are not equal to 1. So that's the second issue. But so I will just show these issues here. So on a very simple case, in a 1D case, here it's the convolution function we want to apply on the model grid with a large convolution length scale. And if we subsample with 1.3, we can still represent the signal. But if we go 1.6, it's fine. Over 12, over 12, it's still okay. We start to distort a bit the signal, but it's still good. But if we have a sharp function with a small convolution length scale, and we want to represent it on a subgrid, on a subsample grid with 1.3, it's okay. Over 6, well, not that good. And with 1.12, then it's not, we are not really representing the shape of the function. So this means that we need an adaptive subgrid depending on the length scale. And so here is the NICAS method. So it's for normalized interpolated convolution from an adaptive subgrid. And it's given by this formula. So you see in green, the convolution on the subsample grid in the center. Then the red SR is the interpolation and its transpose on the other side. And the N matrix in orange is the normalization matrix. So it will make sure that the diagonal coefficients of the final C tilde are exactly 1. And that's for the formula. And another important aspect of the NICAS method is the subgrid. We don't choose the subgrid randomly. It's locally adapted to the convolution length scale. So if the length scale is heterogeneous, as we saw yesterday, we can compute heterogeneous localization or correlation length scales with the HDiag driver of bump. Then we can apply them here, and we can adapt the subgrid used for the green CES for the subgrid. We can adapt this subsampling given the length scale. So if the length scale is short, points will be less subsample, we'll keep more points. And if the length scale is large, then we can just keep a few points, and it will be enough to represent the function. Okay, so to illustrate how NICAS works, I will give an example of an adaptive subgrid, and then we'll follow the steps of applying a Dirac test. I like Dirac test because when you are working with B matrices, it's really the way to understand what your matrix is doing when you apply it on a vector. So the Dirac vector is very simple. It's 0 everywhere and 1 in just one coefficient. And so basically what you see when you apply your operators on this vector is a column of your complete operator. So it's very convenient. So here is the localization support radius that we computed yesterday with the HDiag method. And it has been interpolated on the model grid. And here is, for instance, an adaptive subgrid where you can see that in the white areas where the length scale is smaller, we will keep more points. And in the dark red areas where the length scale is larger, we will keep less points and so have a coarser adaptive subgrid. So now for a given location, I will follow the different steps of applying the NICAS method to a vector. So here the red point, it's 1 at a given location and it's 0 everywhere else. So it's just the initial Dirac vector. Then I apply the normalization. Since it's a diagonal matrix applied on a 1 somewhere, it just changed the value of the point, but it's not very impressive. Then I apply the adjoint of the interpolation. Here it's barycentric interpolation, so with three different points. So when I apply the adjoint, I spread the signal over these 3 different points. And then I do the convolution. So from the interpolation, from the previous steps to the next one, I really spread the signal with this CS matrix, which is a normalized convolution interpolator on the subgrid. Next, I need to re-interpolate on the full grid. So that's what is done here with the red S. And finally, I apply the normalization operator. And at the end, I can check that the peak of my convolution function is exactly 1. So the method is exactly normalized. So I will show you the results of a direct test here. So just remember here over Indonesia and the equator, the length scales are smaller, and south of Australia, the length scales are larger. And if we apply the NICAS method for different Dirac points, so here you can see that the length scale will be smaller over Indonesia and larger over Western Australia, for instance. So the method is working. We can apply an heterogeneous convolution operator using this subgrid, and the functions are not too distorted. There is a strong impact of the subgrid resolution. On the top panels, I have a pretty dense subgrid. And so if I look at the result on the right, the convolution functions are pretty clean. And on the bottom panels, I have a coarser subgrid. So it's still denser in the white areas and coarser in the red areas, but overall I keep less points, smaller number of points. So the final cost of the method will be cheaper. But if you look on the bottom panel, on the right panel, the functions are a bit bumpy. They are not very clean. And maybe it's not a problem because when we apply a localization, we don't really care if the function is very clean. So maybe it's good enough for our system. It's something we have to check and to verify with different tests. But we have a simple trade-off between the cost and the accuracy of the method. So we just have one parameter in the resolution parameter for the subgrid in the bump parameter that can adjust the subgrid density, the overall density. Okay, so another interesting aspect of the NICAS smoother is that since we work with explicit convolution and explicit interpolation in grid space, we can take complex boundaries into account. And so this is very important for the ocean, for instance, where we have complex boundaries, but it can also be interesting for ground, continental surface models where we have also complex boundaries on the other side. And it can be interesting also for limited area models. And here in this example, I have used anisotropic functions. So we can see that it's not, they are not isotropic. Depending on the direction, I can have different length scales. And this is a possible option also of the NICAS smoother. So here it's a comparison between the implicit diffusion method that is implemented in NIMOVAR. So NIMOVAR, it's the variational DA system for the ocean model NEMO. And on the top panel, it's implicit diffusion, and on the bottom panel, it's NICAS. And we can see that the results are not exactly the same, but they are pretty close, and the complex boundaries are correctly taken into account. The main difference is that the NICAS method is about 50 to 100 times faster than the implicit diffusion. So that's a good point for NICAS. So I showed you the basic NICAS formulation, the top formula, but actually what I do in the code, as I said yesterday, is to build the correlation matrix in the center as U transpose. So I use the square root of this matrix, and doing that, I make sure that the full CS matrix is positive and definite. So since I have the square root of CS, of the green CS, it's easy to get a square root of the full C tilde, so of the full NICAS matrix. And this can be very useful for square root preconditionings or for randomization methods. So that's what I said. It's positive semi-definite with this formula. And I need to get a square root of the Gasparian cone function formulation that I use for NICAS2. And it appears that since it's close to the Gaussian, it's its own square root. You just have to multiply by the length scale by an empirical factor, and you get a good approximation of the Gasparian cone function square root. So finally, I'll talk about the MPI communications in NICAS because it's really important to have a method that scales correctly, because if you think about the static B or the localization, it will be applied each time you apply B, and you apply B at least once for every iteration of your minimization. So you will have to apply these operators a lot of times when you do some variational DA. So it has to be very fast and scalable. And an important point of NICAS is that the communications are always performed on the subgrid. So on the subsample grid, that is a lot smaller than the full grid. And so the cost of MPI communications is lower. And we do only local communications between the different allos of the different processors domains. And there is no global communications required, as it is the case, for instance, in spectral methods. Also, we have an option in NICAS to do the MPI communications in different locations, and we can do it in one, two, or three communication steps. And it's easy to show that the more communication steps we do, the smaller the allos required for each processor. So it's a trade-off between the number of communication steps and the memory required for each allo. And also to finally improve the cost, the efficiency of NICAS, I have implemented a few OpenMP loops to get a hybrid parallelization. Okay, so this was for the NICAS smoother that you will use in BUMP. And now I will show you how to use BUMP in OOPS with just a few examples. So BUMP is fully interfaced with OOPS, and the BUMP parameters are fed in this YAML files. So it's these configuration files we use to set up all the other parameters of the variational or any other jobs, and you can set the BUMP parameters in the same files. You can have a look of the default parameters and the short descriptions of all the BUMP parameters in this BUMP /typenam.f90 file. And also there is a documentation here. It's the address of the Sabre repo, but you have a link to the read the doc of the JCSDA, so all the documentation repo for the JCSDA. And you can, of course, send me emails if you need any help on BUMP. I'll be glad to help you. So to get started, we'll see some examples of BUMP for a static B and then for an ensemble or hybrid B. So here is just the section of the YAML files that will be necessary to run the NICAS smoother, so that we just saw for a correlation operator. And here we don't use a length scale that we would have computed before with HDiag, the other driver of BUMP. We prescribe it in the YAML file. So that's a good way to start. And so you will need to specify a data directory, and we will have to tell them that we force the length scales. The method parameter is either correlation or localization. Here it's a correlation operator. We can choose the number of communication steps, so MPI com. we say say to BUMP that we want a new NICAS operator, and maybe the two other important parameters are RH and RV. So RH is the horizontal support of the Gasparin function, and RV is a vertical support radius. RV is defined in the unit of the, the vertical unit that you specify for your model. So depending on the model, it can be either pressure or height or sigma coordinates. It really depends on your model. And for RH, so the horizontal support radius, it's in meters. And the final important parameter is resol, so the subgrid resolution. And it's this trade-off parameters between the cost and the clean, the smoothness of the function you will apply with NICAS. So if we want to compute the covariance, the correlation length scale with the JEDI driver, and we can also compute the variance with the VAR driver using an ensemble, we have to add a few more parameters. So here we ask for a new JEDI diagnostic and new VAR for the new variance computations. So the variance is required for the sigma operators that I showed you yesterday, the standard deviations that are on both sides of the correlation matrix for the static B. In the important parameters to diagnose the length scales, you can see the horizontal bin size, because we will compute the function with different bins. So DC, the size of the subsampling for HDiag and C1, and also the number of diagnostic bins. So basically the product NC3 by DC, it's the total length of your diagnostics, and it should be about around the length scale of your function. And it is also possible to add some keys in this YAML file to filter the variance field that you are computing, because if you have a small ensemble, the variance field is noisy and you can filter it. And there is an optimal iterative filtering option in BUMP. But you can go in the typenam.f90 file and see the possible keys for that. So if you want to use edge diagnostic in NICAS, so you can do both runs at the same time. And here I didn't specify RH and RV, the horizontal and vertical length scale. They are computed within HDiag and then passed to NICAS, and NICAS use them to compute the correlation operator that you will apply in your variational application. So in the same run, you can run HDiag to estimate the correlation radius. You can use the length scales computed by HDiag to set up the NICAS smoother, and you can run VAR, so the variance driver, to estimate the variance field, and you can also filter it. You can once you have this is an important point. When you want to use BUMP in a variational application, you have to do a first pre-calculation step. So you have to do two steps. A first step where you pre-compute the BUMP correlation or localization matrix, and then you will apply it in your variational application. But you really have to do these two steps sequentially. So the examples 1, 2, and 3 were useful for the first step to compute the BUMP parameters. And here in this example, we just load the pre-computed NICAS and variance files, and we use them in a variational application, for instance. So you can see that there is no new NICAS anymore, but a load NICAS to load the pre-computed NICAS files. And you just have to specify the same prefix and data directory, and the same strategy and number of MPI communications, and that's all. The code can read the right file and use it. So that's for the correlation, the first bump section. And if you want to apply the variance that we computed before with the ensemble as the standard deviation operator of your static B matrix, you will need to specify it as a variable change, because basically it's just a diagonal matrix, so it's a simple variable change. And so you will have to specify the standard dev variable change, set the input and output variables that should be the same, and also give the data directory and prefix of your experiment. And the load var option says that the variance files will be loaded in bump and they will be applied for the standard deviation operator. Okay, so all the previous examples, they can be reused for the localization of an ensemble B. So they were more focused on a static B, but for an ensemble B, it's quite the same parameters actually. You just need to update two keys. The first one is the method parameter. So it was core for correlation, and now you have to switch it to loc for localization. And if you want, you can also change the strategy parameter. So in the previous examples, yes, the strategy, it's the last parameter here, for instance, was specific univariate. It means that each variable has its own specific and univariate autocovariance matrix. But for the localization in general, we want to apply the same localization for all variables. And so there is another strategy that is useful, and it's called common. So you specify the common strategy, and it will be good for localization. If you want to get a hybrid B with bump, you have to set the method at hype.rnd for randomized, and you have to randomize your static B to provide a pseudo ensemble. It's a bit more advanced, but it's also possible with bump. And if you want to see some examples of YAML files for these different applications, you can look at the QG model that is implemented in OOPS. And if you go to Sabre, to the bump directory of Sabre, the QG model is also used for tests, and you can have a look at the YAML files. And there are a lot of other advanced bump features that can be activated from the YAML file, but they would be beyond the scope of this talk. Okay, so I'm done for today. It was a bit shorter, and I'll be glad to answer your questions. Thanks.